Hello, I am Aliite Costi. I am at your service with the fourth PLCLS training session. In today's tutorial, we are going to learn more about how to address the digital inputs and outputs of a PLC. Well, in the previous lessons, we said that if we want to assign an address to one of the PLC inputs, for example, input number 1, we used 90.0.1. We said that the I indicates inputs. The X indicates a bit address. The first 0 that we put indicates the base number, or our base number, which in compact PLCs isn't really used, and in compact PLCs this base number is always 0. The second 0 refers to the slot number, which comes into play if we add an expansion card to our PLC. We need to enter its slot number here. And finally, the last number we put here is related to our terminal number. That is the input number on the terminal that we need to specify here. Since we want to address input 1 here, that's the number we put. So here we put the number 1, and also regarding the outputs, as we mentioned, if we want to assign a value to one of the outputs of the S7 PLC, we use the address QX0.0.1, which here corresponds to our output number 1. The Q that you see here indicates the outputs of the PLC. The X represents the outputs in bit format. We already explained the first 0. We said it's the base number, and in compact PLCs it's always 0. The second 0 is the slot number, in case we add an output card to this PLC. We enter its slot number here, and finally, this one you see here refers to the terminal number. So here we're now assigning an address to output Q1. So here we have an LS PLC, and we've added an input expansion card to it. And now we want to assign an address to its input number 5. We use the address 90.1.5. The 0, as we said, indicates the base, and it's always 0 in compact PLCs. This one, as we said, is the slot number, since here we've added an expansion card. We've entered the slot number here. And this 5 is the terminal number of our expansion card. Now here we have another LS PLC, for which we've used 2 expansion cards. A digital input card and a digital output card. Now we want to assign an address to one of these outputs. For example, output number 10, the address we give it is QX0.2.10. So this Q is for outputs, X refers to bit addressing, meaning we want to assign an address to just one of these outputs. The first 0, as we said, is the base number, which is always 0 in compact PLCs. Now this 2 that you see here is actually the slot number, the card that is our output card installed in the PLC. Since we installed it in slot number 2, we set the slot number here to 2. And this is our terminal number because we want to assign the address to output number 10. So here we've set its value to 10. Alright, now let's suppose we have an LS PLC. We've connected several sensors to its inputs. What we want to do is to have the values of these inputs all together in the PLC and read their values. The way addressing functions and operates when, for example, we are utilizing a single byte is structured in this manner. Suppose we have meticulously connected various sensors to I0 through I7, which collectively constitute a complete byte, and we are indeed expected to precisely read the values of these 8 distinct inputs all at once. So the precise method by which we address these is as follows. I byte 0.0.0 Now let's go through these together. So, I indicates input. This B that you see here stands for byte. This time it means we're going to read 8 inputs, that is 1 byte of inputs all at once, and the first 0 is our base number. The second 0 is the slot number, and finally this last 0 you see here refers to our first byte. Let me just mention that the PLC we're using here, it's an XC-DR32H. This PLC has 16 inputs and 16 outputs. That means we can divide its inputs into 2 bytes. So when we set the last number here to 0, it refers to our first byte. Now, if we want to address the second byte, it would be like this. That means from input number 8 to input number 15, it's the same way. I byte 0.0.1. This last one indicates our second 8 bits, or our second byte. Okay, suppose we have an LSPLC with a relay output, model XCDR32H, and we've connected 8 lamps to its outputs. What we ultimately want to achieve is to turn all these 8 individual lamps on simultaneously at once, or to turn them all completely off at once in a synchronized manner. We want to clearly see and understand how to properly address the various outputs when we want to precisely control all 8 of our individual outputs at once simultaneously. So let's suppose, for the sake of this discussion, that we specifically want to address and manage outputs starting from number 0 all the way through to number 7, encompassing all of them simultaneously and at once. The way to address them is like this: Q byte 0.0.0. So when we use the term byte, meaning we are addressing 8 distinct digital outputs at once as a unified group, this very last 0 that we've precisely put here indicates the first 8 individual bits of our overall outputs. Because we said that this PLC has 16 outputs, and we can divide its outputs into 2 bytes or 16 bits. So when we set the last digit here to 0, it means the first 8 bits, or better to say our first 8 outputs. Now, if we want to address the second byte, or the second 8 bits, or the second 8 outputs all at once, it would be done like this. That is, from output Q8 to output Q15, this is how you address them. Q byte 0.0.1. So the initial part of this address is just like the previous ones, but this final 1 indicates our second 8 bits, or our second byte, or our second set of 8 outputs. Now let's write a program together. Suppose we have a start button. We've connected it to input number 8 of our PLC, and we've also connected 8 lamps to the outputs Q0 to Q7 of the PLC. We want to write a program so that when we press the start button, all 8 lamps turn on at once, and when we release the start button, the lamps turn off. So to write this program, first we need to create a byte which will serve as a fundamental building block. We say that from bit 0 to bit 7, they are supposed to turn on. So that means from bit 0 to bit 7, we should have ones. Now we'll write this number in binary form, which gives us our binary number. Later, we need to convert this to decimal. If we want to convert this binary number to decimal, the way to do it is like this. And in the end, the value we get is 255 in decimal. Alright, let's go to the XG5000 software and write this program together. Okay, now we enter the XG5000 software environment. For this, we need the move function. in the XG5000 software to access functions and function blocks. If we click on this option and then click on the main page of our program, a window will open for us where we can select functions or function blocks, or even both functions and function blocks. We can call them here. If we press the F key on our laptop or computer, this window will also appear for us. Well, since I want to use a function here, I'll set it to the function section. As you can see, there's a search bar at the top here, and we can search for the function we have in mind right here. So I want to use the MOV function, so MOV here. I search for it. I click OK on this. The MOV function has now appeared for us on the GX5000 software screen. So this function works by having one input and one output. Whatever value we put in the input, it moves it. For the output, the important point is that the data type of the input and the data type we set for the output must be the same. For example, if we select an integer as the input, then our output also has to be an integer. Or, for instance, we can't set the input as a time and have the output be an integer. The input and output data types absolutely have to match. Another important point is that this function has an enable. When we set its enable to 1, the move operation is performed. That means the input data is moved into the output. So, in order to write the program we had in mind, we use a normally open contact and place it in the enable part of this function. And we put the address of the start button here. That is to say 90.0.8, because we have connected the start button to input number 8 of the programmable logic controller PLC. So the number we converted to decimal together was 255. I moved the number 255 into QB 0.0.0. So with this program, in fact, 255, which is in decimal, is moved into QB 0.0.0. And as we explained, it sets all 8 bits, that is one whole byte, completely to 1. And that's exactly what we wanted, meaning the first byte or the first 8 bits of our outputs, that is Q0 to Q7, are set to 1. When this function of ours is enabled, that is, when we set input number 8 of the PLC to 1, this function gets enabled and this value is set inside our PLC. Well, this program works momentarily, meaning as long as our finger is on the start button, the first 8 outputs of our PLC are set to 1, and when we lift our finger off the start button, those 8 outputs go to 0 and our lamps turn off. Now we have an LS model PLC. This time what we want to do is read the values of all 16 inputs of this PLC. That is from input number 0 to input number 15 all at once. Now let's see how the addressing for that works. So the addressing for that would be W.0.0.0, where the W you see here stands for word. The first 0 is our base number. The second 0 is the slot number, and the last 0 refers to the first 16 bits of our inputs. Now, if our PLC was a DR64H instead of a DR32H, in that case, instead of 16 inputs, we would have 32 inputs. At that point, if we wanted to read the second set of 16, the last 0 would be replaced with a 1. Alright, now if in this same PLC, that is the XCDR32H, we want to command all 16 of its outputs at once, meaning we want to address and command Q0 to Q15 all together like this. The way to address it is keyword 0.0.0, which, well, all of these are similar to the previous ones, except that the last 0 here represents 16 outputs. That becomes our first output. And now, as we said, if instead of this PLC we use the DR64H, and we want to address the second set of 16 outputs all at once, what we need to do is replace that last 0 with a 1. So all the PLCs we've looked at so far have been compact PLCs. Compact PLCs, as the name suggests, are PLCs where the power supply, CPU, and input-output cards are all housed together in one package. Well, in addition to compact PLCs, LS Company has also produced another type of PLC called rack-type PLCs or modular PLCs. Now we're going to get familiar with those PLCs as well, and we'll also take a look together at how to address the input and output cards of those PLCs. Rack-type or modular PLCs are PLCs that consist of a rack and the power supply CPU and the modules we need like input cards, output cards, temperature cards, network cards, and any other cards we use in our PLC all get mounted on the rack. In compact PLCs, the advantage they have over modular PLCs is that the CPU is upgradable. That means you can remove the CPU card from the rack and replace it with another CPU. So if this CPU is too weak for you and you need a more powerful one, you can replace the CPU. Also, in these PLCs, we can use multiple racks, and the number of modules we can use in rack-type PLCs is greater than in compact PLCs. Usually in situations where we have a large number of I/OS, that is, a lot of digital inputs and outputs, or when we need to use many modules in the program, we use rack-type or modular PLCs. Well, as we have previously mentioned, modular PLCs typically consist of a power supply unit, a central processing unit (CPU), and in the specific model you observe in the accompanying picture, there is one dedicated input card and one dedicated output card. Also, as I mentioned before, the ability to add racks exists in modular PLCs. In modular PLCs, depending on the type of CPU we use, we can connect up to a maximum of 7 racks together using cables. In this picture, in the upper rack, we've used a power supply, a CPU, an input card, and an output card, and we've connected the upper rack to the lower rack with a cable. In the second rack, or the external rack, or the expansion rack, we only use a power supply and there's no need to use another CPU. We can place the modules we need onto the rack. For example, input and output cards. Alright, now let's take a look together at how to address the inputs and outputs of rack-type PLCs. So when we use multiple racks, we call our main rack base 0, and the rest are numbered starting from 1. Now suppose that in our base 0, or perhaps more specifically rack 0, we currently have an input card installed, and we genuinely want to assign a unique address to one of its various inputs. For example, for input number 4, the addressing would be like this: 90.1.4. So I indicates our input, X shows that it's a bit input, meaning we only want to use one of the inputs. This first 0 indicates the number of our base or rack, and as we said, our main rack is always numbered 0. This one that you see here refers to our slot number, because we've placed the input card in slot number 1. So here, our slot number is 1, and this number 4 is input number 4. In fact, our card, meaning our terminal number, becomes this, because we used input number 4. So here the number 4 is placed. Now, suppose we want to assign an address to output number 12 of this output card. Its address would be like this. It would be QX0.22. The Q indicates outputs. The X indicates a bit output, or a single output. For us, 0 is the rack number or the base number, and since this is our main rack, we set its number to 0. 2 is the slot number because we installed the output card in slot number 2, so we put the slot number as 2 here. And finally, we have the number 12, which specifically refers to our 12th and final output in this sequence. Now, suppose for a moment that we want to precisely assign a particular address to input number 6, which is located within rack number 1, or more precisely, our designated base number 1. It would be IX1.1.6. Well, this shows that the I indicates our input. X indicates one of our inputs, meaning it is in bit form. That is, we are supposed to assign an address to just one of the inputs. This is our base number because we used rack number 1, so this is the base number. The second part you see here is our slot number, so whichever slot we installed the card in, we need to enter that slot number here. And finally, the 6 you see here refers to our input number 6, meaning it corresponds to the terminal number of our input card. Now, suppose we want to assign an address to Q0 from our second card, which is the output card. This is how its address is formed. QX 1.2.0. Q indicates the outputs. X shows that the addressing is done in bits. 1 refers to rack number 1, or our first base. 2 indicates the slot number, and since it's installed on slot 2 here, we've set it to 2. Finally, the last 0 refers to the output terminal we're using. Since we're using output Q0, that's why we put 0 here. That is all for this session. Thank you.